everyone. Welcome to GALOP'. It's my pleasure to introduce Ugo Dal Lago for the first talk of GALOP', and he will talk about interaction efficiency and reversibility.
Thank you very much. It's a pleasure and an honor to be here, and I'm very glad that GALOP' is back after a few years of interruption due to the pandemic and other issues. Yes, I want to talk about a series of joint works I've done in the last 3 years with co-authors Beniamino Accatoli and Gabriele Vanoni. And actually, the title of the talk is not really like appropriate. I cheated a bit. Rather than talking really about efficiency, what I will talk about is invariance. I decided not to put invariance in the title because it's a kind of an overloaded word, and the first thing I want to do is to explain to you what I mean by invariance. So, when you have a computational model, you typically see it as a transition system in which, from the initial state for an input x, you progressively go towards a final state for the output fx, this way computing a function. And what you insist on is that the intermediate steps are all effective enough, are elementary enough, so that the whole thing can be seen as an algorithm, as an implementation of an algorithm. But typically, when you are also interested in efficiency, you go beyond that, and you also require that the number of transitions is taken to be the time. So it's even more important that each transition is elementary. And you also consider the maximum size of the visited configurations, excluding typically the space needed to store the input and the output as a measure of space. And well, this has been done for many different computational models, including Turing machines, random access machines, and the starting point of all these works was the following question: can we do that for functional programs and lambda terms? Can we see functional programs and lambda terms as a proper computational model, namely a model in which also time and space can be measured, can be considered? And actually, there is like a thesis about how and when a computational model can be considered reasonable from the point of view of time and space measures. And this is due to Slot and Van Emde Boas, who in the 80s proposed this invariant thesis formulated as you see. This is a relational property rather than a property about one computational model. And what it says is that reasonable machines simulate each other with a polynomial overhead in time and a constant factor overhead in space. So one machine can simulate the other in this big class of invariant and reasonable computational models if there is a polynomial overhead in time and a constant factor overhead in space. And this is pretty much a standard notion of invariance for computational models. But why? Why are we taking it? What is it that it is invariant in the invariance thesis? Actually, what stays invariant is the notion of polynomial time. Because if the overhead is polynomial, of course, you can then define the notion of a polytime computable functions in any of the many computational models which you prove reasonable, and you obtain the same class, which is what really stays invariant. And also logarithmic space stays invariant because the constant factor overhead in space allows you to do so. So this way, polynomial time and logarithmic space becomes robust. And this is precisely what you observe in practice. A class which is not robust instead is, for example, the class of quadratic time computable functions. In different computational models, this is simply different. Okay, great. So the thing is that if you want to prove the lambda calculus or functional programs to form an invariant cost model, well, this is going to be difficult, and this is difficult because of the size explosion problem. And the size explosion problem, it shows up in all kinds of different dialects of the lambda calculus, even in presence of types, independently on the strategy you use. What does it mean? It means that it's very easy to form families of terms Tn such that the size of the family is linear. Each term in the family rewrites in a number of steps equal to n, to a term, typically a normal form. But what is bad is that the size of the normal form or the size of the result is exponential in n. So in a linear amount of steps, you get to a term which is big, which is too big. So this means that if you consider the lambda calculus as a computational model where the measure of time is the number of beta steps, well, things are complicated, and this is not something you can prove invariant easily, okay? Because of the size explosion problem. So this is the background, and we have worked a lot on all these problems, even before the series of work I was referring to. And okay, let's take a look, for example, at time invariance, at how we can try to achieve a time invariance for the lambda calculus. And you can try to avoid the size explosion problem by going through abstract machines, and you can consider, for example, the Krivin's abstract machine as one of the simplest abstract machine for the lambda calculus. Actually, it's based on triples of term configurations are triples of a term and of an environment and a closure. Term, environments, and stacks. And environments are sequences, can be seen as sequences of closures. And I'm sure you have seen the Krivin abstract machine many times. There are just 3 rules. Each of the 3 rules are concerned with one of the 3 operators of the lambda calculus. So applications, abstractions, and variables. And what is interesting here is that the crucial invariant that all terms you find in the first position of configurations are subterms of the initial term holds. And this is a very interesting and important invariant. In particular, this allows you to keep the size of the term you manage under control. And ultimately, this is what allows you to prove that the number of reduction steps of the Krivin abstract machine is a reasonable time cost model. Okay. So yes, by way of abstract machines, you can at least give a notion of reasonable computational model over the lambda calculus, even if it's not really the number of beta reduction. Good. Well, can we kind of see, can we kind of capture what's going on in the Krivin abstract machine by way of types? Well, since the types you find in the first component of your configurations are subterms of the initial term, of course, if the starting term is simply typable, well, even all the subterms you encounter are simply typable, and there's more. The subterm you find in the first component of the configuration along computation in the Krivin abstract machines, well, they are part of your type derivation, of course, because they are subterms of the initial term. The point is that this correspondence is not injective, so the type derivation can be much smaller and much more compressed than the whole the whole computation. Okay, so you can have a small type derivations corresponding to very, very long computations. And you can try to go towards a notion of typing which is more quantitative by way of multi-types, or if you like, non-idempotent intersection types. And in non-idempotent intersection types, I mean, the key idea is that, well, to the left of the arrow, you do not have a type, but you have a multiset of type, and each of the elements of this multiset accounts for a possible use of the argument. And of course, all the possible uses of the argument, can be given different types. And yes, apart from that, the type system is pretty standard. Well, if you know intersection types, the only difference with the usual idempotent intersection types is that when you form the intersection, well, the number of copies counts, and it's so idempotency does not hold. But apart from that, if you employ non-idempotent intersection types, there is now an injection between the configurations you find in your computations and the sub-type derivations. So the type derivation is as big as the computation, which is nice. Indeed, this way you can use multi-types, you can use non-idempotent intersection types as a way to study the quantitative behavior of your term when evaluated with the Krivine abstract machine. Indeed, you can give a weight to each term by labeling typing judgments with natural numbers. And you do that by just counting the number of rule instances in the type derivation, and weights are just summed up when computing the labels. And this way, as proved by the Carvalho, like almost 20 years ago, every closed term T can be typed in intersection types with labels W, if and only if the term can be reduced in n steps with the Krivine abstract machine. So not only you have a reasonable time cost model, but the time, the crucial parameter, can be captured by way of non-idempotent intersection types. But then, you may wonder, well, where's interaction? Why do we put interaction in the title of this talk? And where are games? Because we are at GALOP', so we would like to take a look at things like games, game semantics, or the geometry of interaction. So let's take a look at how you can try to go towards geometry of interaction starting from the Krivine abstract machine. And this is like the first thing we did together with Gabriele and Mediamino. So we derived the interaction abstract machine as an abstract machine on the lambda calculus from the CAM, from the Krivine abstract machine. So if you start from the Krivine abstract machine, and you can first of all do a completely armless operation, namely, well, since all terms are subterm of an initial term, you can just decorate the configurations with a context. And the context tells you where in the initial term you find yourself. Well, this is totally armless. This is, just to mark where in the initial term you find yourself. But then, you can do the following. In the first and second steps, in the first and second rule of the Krivine abstract machine, you can decide. You do not want to remember. You do not want to. Okay, you do not want to remember, the argument when you go to the left in an abstraction. You just forget it because you want to be space efficient, and you don't want to keep it with you along the computation. You just mark the fact that you go to the left with a bullet. Okay. And then, you know, when you encounter an abstraction, you just throw away this bullet because you are in the body of the function. The point is that if you do so and you arrive in a variable, well, you don't know where to go because you forgot the arguments when going down in the spine, right? So you need to reconstruct the argument when you arrive at the variable. And you know, if you do so by just remembering the least information possible, you get a machine like this, okay, where you know you keep working with 4 components: a term, a context, sort of an environment, and a stack. But of course, the machine is going to be different. It's different because of 2 reasons. The first one is that the computation is reversible now, because you never really throw away essential parts of the computation. And the second thing is that you use something called exponential signatures. Exponential signatures are there to remember in which copy of a potentially copyable term you find yourself. Okay? And it's the minimal amount of information that allows you to do so. Good. So if you are used to the interaction abstract machine as derived from linear logic through proof nets, well, this might sound a bit unfamiliar to you. It's you know, superficially it's very different, but there is a way to prove that it is isomorphic. Actually, it's the same thing. Okay, the number of so the transitions you make are precisely those induced by proof nets. The only thing is that when you find yourself in an exponential in a tree of contractions, you just traverse the tree in one step rather than in many steps. Okay, that's the only difference. Good. So this is the interaction abstract machine. Actually, one presentation of the interaction abstract machine, and we may wonder whether this is time invariant, right? Whether this notion of an interaction of an abstract machine is time invariant. And well, the first thing we proved was that, well, there are some improvements while going from the interaction abstract machine to the Krivin abstract machine. Improvement in the sense of sense. So, like there are speed ups. And in the middle between the interaction abstract machines and the Krivin abstract machine, there is the so-called jumping abstract machine, which is an optimized version of the interaction abstract machine, obtained by just jumping over some of the transitions, if you like. And already from the IAM to the JAM, we have a potential exponential blow up, or better, a speed up. So the jumping abstract machine can be exponentially better than the interaction abstract machine. So already here you see that, well, the interaction abstract machine can be very time inefficient. And well, from the jumping abstract machine then to the CAM, you get a quadratic speed up, potentially. Not for all terms, of course, but at the most a quadratic speed up. And well, but then is it that even if we get an exponential speed up when going from the IAM to the JAM, or is it that, well, there is any hope to prove that the IAM is at least time invariant? Well, not really. We can do that by just exploiting again intersection types. So you can use multi-types not only to account for the time complexity of the Krivin abstract machine, but also of the interaction abstract machine. Why? Because you just you simply change the way you give weights to type derivations. The type derivations are always the same. You just change the way you attribute weights to them. Instead of counting the number of rule instances, you just count the size of all types occurring in the type derivation, and you sum them up. Okay? And this is a precise, faithful measure of time reflecting the one of the interaction abstract machine, precisely. Okay? So rather than counting just one for every rule instances, well, you need to count all types occurring in the type derivation. And why is this relevant? Well, because then you can take a look at the encoding of Turing machines into lambda terms. Why are we looking at that? Well, because if you want to prove the interaction abstract machine time invariant, you need to prove that Turing machines and the YAM simulate each other with a polynomial overhead in time. And then you have to prove that Turing machines can be embedded into lambda terms with a polynomial overhead, as far as the YAM is concerned, the IAM is concerned. But if you do so, you notice that, well, the encoding of Turing machines invariably makes use of fixed point combinators. And the fixed point combinators are quite bad as far as their multi-types are concerned. We can easily realize by just looking at the type derivation for encodings of Turing machines that the fixed point combinators get exponentially big as far as their types are concerned. What does it mean? Well, it means that there is no hope, right? That it means that the interaction abstract machine, when run on TM, will take a number of steps which is exponential in the number of steps of the original machine. So, nope. There is no hope to get invariance. So the interaction abstract machine then is not invariant, at least if you focus on, let's say, natural encodings of Turing machines into the lambda calculus, and if you consider the natural time cost models for them. Great. So let's take a look at space invariance briefly. So is it that the interaction abstract machine is space invariant at least? It's not time invariant, we know, at least if you consider natural encodings. But you know, people have for a long time hoped that the interaction abstract machine and geometry of interaction can be seen as a space-efficient notion of computation. This is, a quote from the original paper by Jan Mackey on the geometry of interaction machine. And as you can see, well, he was hoping that even if time inefficient, when he refers to efficiency, I think he refers to time inefficiency towards the end. Even if time inefficient, well, at least the geometry of interaction machine can be space efficient. So let's take a look at the interaction abstract machine, and let's consider the problem of measuring their time complexity. So the key observation here is that, well, in exponential signatures, there could be many occurrences of the original term. Okay, in one exponential signature, there could be many occurrences of the original term, and each of them, of course, is takes some space. we need to keep track of them, and they take some space. The thing is that exponential signatures correspond in multi-types to multisets, and the multisets are just flat. So if you want to reflect the fact that many subterms of the initial term can be found in the same exponential signature, we have to change a little bit our notion of typing. And this is what we do by three types. Three types are just non-important intersection types where multisets are replaced by trees. Okay, so they are nested. They are not just plain flat multisets, but they are nested multisets, if you like. And well, if you do so, the type system can be easily modified. When you, for example, whenever you flatten multiset, you don't do that anymore, and you keep the nesting explicit. Nesting indeed is allowed, and this way you can reflect the space consumption of the interaction abstract machine into types. Why? Because now you have a slightly different type system. Whenever you give the new way you have to give weights to terms is just exploits in an essential way the presence of three types. In particular, the shape of three types tells you how many pointers to the initial term you have, and this accounts for space. Crucially, rather than summing the number of pointers up, you just take the max, okay? Because you are interested in space rather than in time. And what you can prove is that, again, this is a faithful representation of the underlying computation, which keeps track of space the way you want without losing any information. But again, why are we doing so? We are doing so because this allows you to study space invariance, right? Why? Because if you take a look again at the encoding of Turing machines into lambda terms, you would like this embedding of Turing machines into lambda term to induce a constant factor overhead, because this is what the invariance thesis tells you. And what happens? Well, it happens that nope. Because again, the use of fixed point combinators induces the following observation. Particularly, the number, the amount of space the encoding of M uses is at least proportional to the length of the computation. So it is impossible then, if you embed the Turing machines this way, to have some linear space, to have to use an amount of space which is significantly less than the number of transitions, than time. And this is, of course, something you want to do. Imagine, think about logarithmic space. Well, logarithmic space is interesting because of that, right? Because the space used by the computation is less than the size of the input, and that's it. Okay, great. So the YAM cannot even be considered as a space invariant. Not time invariant nor space invariant, at least if you consider this kind of encodings. Okay, and then just briefly, let me briefly take a look at the CAM, right? Let's go back to the Krivine-Nastran machine and let's take a look at whether the Krivine-Nastran machine can be considered as space space invariant. Well, if you consider one such computation, a computation in the CAM, there is, first of all, the fact that typically you share environments. So sharing is used everywhere for the sake of, obtaining a certain level of efficiency. But this makes space unaccountable, because as you start using sharing in a wild way, you just there are environments which are heavily shared by other environments, for example, and keeping them into account becomes very complicated. Of course, you can use garbage collection, but in garbage collection can be very space efficient, but it makes space unaccountable. And we of course want to take it into consideration and to measure it. So we want it to be accountable. Okay, now what we did was to slightly change the Krivine abstract machine for the sake of solving this problem, the problem of space unaccountability. And we do it in 3 steps. The first thing is to use a standard folklore optimization called unchaining, which allows you, to just shortcut the computation when the argument to a function is a variable. The second one is that, well, it is the crucial one. Sharing is limited to terms and not to environments. So environments cannot be shared. So whenever you, for example, encounter an application, you really copy the environment. What you don't copy are the pointers to the initial term. And this way, space becomes accountable. And then you do some form of eager garbage collection. So whenever you find an abstraction and you realize that X does not occur free in the body, you just throw away the corresponding closure. And what we proved is that the size of configurations of the new version of the CAM we obtained, the space CAM, is a reasonable space cost model. Okay, and so it can simulate Turing machines with the constant factor overhead. The proof is a bit kind of complex. It's a bit even tedious because you have to distinguish between the part of the initial term corresponding to the input and the part of the initial term corresponding to the actual function when encoding Turing machines. But I don't have time to talk about that. Okay, so I wanted also to talk a little bit about how you can capture the space consumption of the space CAM by way of types, but I don't have so much time. I want to keep the schedule more or less in time. So we can do it by something called the closure types. Let me just spend 1 minute on that. The closure types are yet another variation on the paradigm of non-idempotent intersection types, where what you do is to have an explicit annotation inside the types accounting for the size of closures, because this is your measure of space now. How big the closure is basically, the space consumption of your algorithm, of your term. So you need to do that also at the level of types. You need to reflect that also at the level of types, and you get what you expect, that by way of closure types, you precisely reflect the space computation, the space consumption of the space CAM. Great. So I want to end my talk with a couple of perspectives. This is not at all about published work. This is a couple of observations which came to my mind in the last year or so. I would be happy to discuss with you if you are interested. So the first one is, well, it stems from a look at the literature. So if you, for example, look at this paper, it's by Ulrich Schöpp, 15 years ago. He managed to prove that a variation on bounded linear logic captures logarithmic space. And if you take a look at how Uli did that, well, he used the geometry of interaction. So he managed to prove that by way of the geometry of interaction, you can capture logarithmic space, so sublinear space, first thing. Then me and Uli, we kind of elaborated on that later. We were not using BLL anymore, but again, we managed to to introduce a notion of space-bounded functional programming through the geometry of interaction, achieving sublinear bounds. And on top of it, there is also this work by Damiano Mazza, who managed to use the geometry of interaction to prove that simple parsimonious types can be evaluated in logarithmic space. So, if you remember what I said, namely that the geometry of interaction is kind of incompatible with sublinear space, and you look at these works, well, there seems to be an apparent inconsistency, right? Why am I saying that GOI is incompatible with the sublinear space if there are these works that precisely do that? And I think this is a good question. Maybe, the reason why Mazza, Uli, Ulrich Schöpp, and managed to do that that they consider calculi which are less powerful, less expressive than the plain untyped lambda calculus. And indeed, Mazza, for example, considered parsimonious types, and if you don't know about parsimonious type, what Mazza means by that is that contraction is asymmetric, and maybe this is the reason why sublinear space is achievable. Indeed, if you think about it, having contraction in an asymmetric form means that exponential signature can be represented in an optimized way by just a natural number whose length is logarithmic in the number of copies you do, which is of course not possible in the usual untyped lambda calculus where contraction is binary. Maybe. But then, if you take a look at the work by Uli and also my work with him, well, you realize that the kind of geometry of interaction we use was not really reversible. You remember, the interaction abstract machine, as I presented it, was really reversible. That one was not reversible. Actually, in the proof of completeness for logarithmic space, he was kind of forced to use something called skewed iteration, a form of while loop, if you like, which is not invertible. Okay, so in particular there is the end configuration of the while loop in which two configurations insist in terms of the underlying transition system. So it's not bideterministic. It's not reversible anymore. So maybe irreversibility is another ingredient which makes your life easier when you want to encode sublinear space. So I would very much like to understand all this and the deep reason why there is this inconsistency in the future. And another thing which is actually related to the last observation has to do with reversibility. So the study of reversible computation is long. For example, there are a couple of very famous papers by Bennett in the 70s and 80s, studying in particular the complexity of transforming an irreversible Turing machine into a reversible one. What is the overhead that all this induces? So this is the first paper, and here, he was basically interested in the possibility of turning an irreversible Turing machine into a reversible one. And then, this other one is much more interesting. It shows that there is a kind of a time-space trade-off when doing this operation. You have to either decide to be time efficient and space inefficient, or the other way around. So it seems from the work of Bennett that when you start from a Turing machine, you can get reversible Turing machines of different kinds, and there is this time-space trade-off. Either you are efficient in time or inefficient in space, or vice versa. And my impression is that if you take a look at the CAM versus YAM transformation, you can see it as along these lines. But the point is that you land too much on the right-hand side. You are so time inefficient that you cannot even be space efficient. Okay? And I'm now wondering whether you can redefine the interaction after a machine with this picture in mind, keeping it a little bit more on the left-hand side. Okay, such a way that you are slightly more time efficient and a bit. And this way, maybe you can even get some form of space efficiency. I don't know. It seems really that the current transformation from the Krivin abstract machine to the interaction abstract machine is really even outside of Bennett's spectrum. It's too much on the right-hand side. And I'm taking some inspiration in doing that from some recent work by Sabri and colleagues on compact closed categories, in which they are really interested in reversibility first of all, and in the time-space trade-off. Good. So why? What's that? Oh, yes. Maybe. Let me. Oh, what's that? Oof. Okay. 1 second. I just want to. Okay. Maybe now. Yeah. So to sum up, I think the contributions of our work was, shed some light about the invariance of the interaction after machine, which surprisingly for us, it's not space invariant. Well, the fact that it was not time invariant was expected. And we like very much also the fact that non-idempotent intersection types seems to be like a unifying tool to analyze combinatorial properties of these abstract machines in all these cases. And as I said, I would like to understand whether a notion of interaction after machine which is optimized, it can be proved to be at least time invariant, even if the polynomial overhead is big. And this way, maybe you can also prove it to be space invariant. But I would like to do it by keeping it reversible, because I think this is an added value. Thank you very much.
I was wondering if it would be possible to also study the point abstract machine and have this kind of results too. I mean, what would be your feeling about it?
I think that this is a question that I proposed to Gabriele recently. Yes, it's I think since you can capture the Krivin abstract machine by just counting the number of rule occurrences and the interaction abstract machine by just counting the size of all types, I think the pointer abstract machine can be captured by just looking at part of the type, by just counting for all types, not the whole of it, but some parts of it. So this is just an idea. For the moment, we haven't really looked at the details.
So can you say something about the reversible machines? Like in practice, what kind of places might need a reversibility?
Well, since the 70s, there have been many studies about the role of reversible machines, for example, for energy efficiency, right? Because since the pioneering work by Landauer, we know that if all your operations are reversible, you can keep the energy efficiency of your whole, at least in theory, you can keep it under control much more than when your computation is irreversible. So I think this is still something that people are looking at. It's not maybe as fashionable as some years ago, but and of course, there is always the thing that quantum computation is irreversible. So,
hi.
Yeah.
I've always I think I saw a talk a long time ago which had some sort of like idea of semantics of reversible computation being finite sets and bijections. But I got the impression from this talk, but I might be wrong, that from your point of view, it's more like finite multisets and maybe multiplicity preserving bijections or something like that. But
I would I would say that the role of multisets in our work is not really the same as the role of reversibility. So I will keep the two things separate. So the multisets are in types, and they allow you to count how many times your subterms are used. And in the form of in the case of the interaction after a machine, if you are computing a partial injection because that's it, right? Yeah, I would keep the two things separate. I don't think there is a strong interaction between the two.
Okay, I think it's probably best to go on with the schedule and keep the rest of the questions for offline discussion. So thanks very much, Ugo.
Thank you.